Okay, this is problem P5-123. And it is on page, let's see, page 312 in the 5th edition. It's at the very end of the chapter. The last two problems are the theorem of three moments. It's a fairly small work area here, so I'm going to try and be careful, use my space wisely. Let's start off by drawing the system. The system is a fairly simple system, except that it's statically indeterminate. We've got a distributed load along the entire length of this beam of 50 kilonewtons per meter, but we have three reactions. We have three supports that are not allowed to deflect. There's a reaction at A, reaction at B, and reaction at C. Each one of these is separated by 1.6 meters. So this is a statically indeterminate problem. Remember, our assumptions going into this is that there's no preload. In other words, if we were to take off this 50 kilonewton per meter externally applied load, the reaction at A, B, and C would be simply zero. Notice we're neglecting the weight of the beam as well. Now, the theorem of three moments basically says, well, the beam has to be continuous and each one of these points cannot deflect vertically. And from that, the three-moment equation can be derived and we can use it. So let's write out the theorem of three moments equation, and let's see what all we can throw away, because like I said, most of the time we won't use all of it, at least when we're learning. Because it's so long, I'm going to put the equal sign on the next line and write out the whole thing. Remember, all of these terms have to do with point loads. Don't forget that this is more for the sake of the video, but that parenthesis is missing in most printings. It's for segment 1. And where's segment 1? Well, here's segment 1 from A to B. I guess I'll put a 1 inside there. And here's segment 2 from B to C. Okay? So minus summation Pi Bi over L2 multiplied by L2 squared minus Bi squared quantity in bracket. And finally, minus the distributed load in section 1, L1 cubed divided by 4, minus the distributed load in section 2, L2 cubed, 3 over 4. So from the very beginning, what did I waste time in writing? There's quite a bit that I wasted time in writing, isn't there? Let's start with the left-hand side of the equation. Is there any moment at point A? In other words, if I were to draw a very small segment at point A with our reaction at A and a little bit of distributed load, would there be any moment in the beam? Remember, these are all moments within the beam material. Well, no, right? There's not any moment arm. No significant force. Of course, there's also a shear load here. Okay, but there's no moment to speak of. So the moment at A is zero. Another way of looking at this is that to the left of the support, there's no externally applied loads causing any moment. So the moment at A is zero. Similarly, what other moment is zero? What other moment is zero?
C.
C. So we can get rid of that term as well. Are there any point loads at all in this beam?
No.
No, they're all distributed. So this term goes away, and this term goes away. This term goes away because there are no point loads in segment 1. The second term goes away because there are no point loads in segment 2. Make sense? So we've already been able to simplify our equation quite a lot. We've got 2 times the moment at B multiplied by L1 plus L2 equals negative W1 L1 cubed over 4 minus W2 L2 cubed over 4. Okay? Now the only unknown here really is the moment at point B. So let's solve for that moment. The moment at point B would be equal to negative W1 L1 cubed by 4 minus W2 L2 cubed by 4. And really, I could put these two together, couldn't I, if I wanted to? In fact, well, we'll do that in a minute. There's going to be some simplification because this is such a basic problem. But let's take the factors on MB and put them in the denominator on the other side. Okay. Could we simplify this at all? Well, you notice that W1 and W2 are equal, right? You notice also L1 and L2 are equal. L1 is 1.6 meters, L2 is 1.6 meters. So let me just write this as negative 2 WL cubed over 4. See what I did? I just added these two terms together because I know that W1, W2 are the same, L1, L2 are the same. I just called them W and L instead. We got to be careful here because this L, a lot of times we talk about the entire length of the beam as being L. This L is just half of it because L1 and L2 each are just the lengths of their segments, which happen to be the same in this problem. Okay? So now let's see, if we simplify this down even farther, putting the constants together, let's see, invert and multiply. Let's see, 1/2 would be a quarter. So it's negative WL cubed over 4 L1 plus L2. Make sense? Which, by the way, this L, and this L are all the same. So I guess I could have written 2L instead. Probably should have done that, 2L. Well, we can simplify a little bit further. Minus W, one of the L's will cancel. We'll have L squared over 8. I think that's right. Let me check. Yeah, that's right. So now we can calculate the magnitude of the moment in the beam. Now, let's see. The distributed load is 50 kilonewtons per meter. And L is 1.6 meters. That has to be squared and then divided by 8. When you plug all of this into your calculator, you'll find that the moment at B is negative 16 kilonewton meters. So all of this work to find the moment at B. Okay. Now, remember, like I said, the sign convention here is that counterclockwise is positive. That's what this equation is assuming. And so, what does that mean? Well, if I take the segment, let's take the right-hand face. Let's see, I'm going to have to erase some of this. I don't want to put my diagrams over there. That was my line so I don't go off the video screen. If I were to take the left-hand side with the reaction at A and the distributed load all the way up to, but not including point B, so almost to point B, what else is there? Well, there's also the moment that we just calculated. Counterclockwise is positive, and so, bless you, this is the moment at B, which is negative 16 kilonewton meters. What does that mean? Well, that means the moment B is actually acting in the opposite direction, right? But I'm going to draw it this way in order to keep it clear. Now, if you look at my example problem PDF sheets, I didn't do it that way. I wrote MB in the opposite direction, then flipped the sign in the sum of moments equation. Also, I've got the reaction at B here, but I'm taking a bit different free body. Now, what else? What other load could be here? There could also be some shear, couldn't there? So let me draw the shear in the positive direction. So there's the shear just before point B. Let's call this the shear at point B, I don't know, minus. So just before point B. Now, since we know the magnitude of the moment, we can actually, some moments about B, or just to the left of B, that'll get rid of the shear at B, or just to the left. And we can calculate the reaction at A. So summing moments about point B, we're pretty darn close. Taking counterclockwise as positive, well, RA is going to cause a negative moment. It has a 1.6 meter moment arm. Also, this 50 kilonewton per meter distributed load will cause a moment about B. So it will be a positive moment plus 50 kilonewton meters multiplied by 1.6 meters worth. This bit here gives me the resultant. Okay, the resultant will act at the center because it's a uniformly distributed load. So it has a moment arm of 0.8 meters. So that's where the last 0.8 meters comes from. It's the moment arm of the resultant of the distributed load. Okay? But that's not it. There's also the moment at B. So what I'm going to do, let's see, I just have to add it, negative 16 kilonewton meters. Okay? Notice it's not actually in this direction, it's the opposite direction, which is against the sign convention, so there we go. Now this sum has to come out to 0. That may be a bit off the video screen, hope not. Okay, so solving for the reaction at A, if you go through this, you'll find that it's 30 kilonewtons. You can check, just plug in negative 30 kilonewtons times 1.6 on your calculator, add to it this term and subtract off 16. Double check as I go if you would and make sure I got that right. Keep me honest.
This is a small error. Isn't it 50 kilonewtons per meter?
You're right, thanks. 50 kilonewtons per meter. The units we'll end up with is kilonewtons times meters overall. Thank you for pointing that out. Let me jot down over here that the moment at B is a negative 16 kilonewton meters, so I don't forget it that way. I can erase this. Did it come out? 30 kilonewtons? All right. So there's the reaction at A. We can do the same thing on the other side. Draw a free body diagram. It's going to be too high. We'll draw a free body diagram with the distributed load in segment 2 of 50 kilonewtons per meter. There will be a reaction at C. Now, on this side, I'm taking just a little bit to the right of point B. Now, in what direction is the moment acting? Well, the moment on this face, remember this face is connected to this face. So the shear and moment have to be exactly opposite whatever they are here. Does that make sense? So I would draw VB plus like that. And I would draw the moment at B like this. Again, I've drawn it in the wrong direction because when I plug it into the equation, it's actually going to be, no, actually I've got it in the right direction now. Now it's positive. So now it's 16 kilonewton meters in that direction. Okay? And hang on just a second, let me think. So let's sum moments about B, taking counterclockwise to be positive. That sum should come out to 0. I'm going to run out of space here. We're going to have the reaction at C multiplied by 1.6 meters. Let me drop the units. That'll save me some space. We know it will come out in kilonewtons. So let's see. Counterclockwise positive, RC. Yeah, that works. And the distributed load is going to cause a clockwise moment, so minus 50 kilonewtons per meter, multiplied by 1.6 meters gives me the total resultant load multiplied by 0.8 meters. I'm still running out of space. The last moment to consider is the moment at point B, right? And I said this is simply a positive 16 kilonewton meters, right? Because this is actually the correct direction for the moment. But in the sign convention, that is a negative thing, so I have to subtract 16 kilonewton meters of moment. Does everybody see that? The sign can be kind of confusing. Kind of the right sign can be confusing. The reaction at C, if you do this, comes out to 30 kilonewtons, which is not a surprise. This thing's symmetrical. You really expect RA and RC to be exactly the same, right? Now I'm going to add something that I don't have on my sheet here. I'm going to add what I showed you that I said is actually very valuable, and let me figure out where to put it. I'm trying to make sure that the video can capture this. I'll try to write this way. I'm going to add the segment that includes the reaction at B. Notice that I mentioned connecting this side to this side, but really I could separate those two into a very small segment that connects to this free body and a segment that connects to this free body on the right-hand side. That would be more appropriate, because what about the effect of RB? Couldn't that possibly affect the moment in the shear? Of course it could. Okay. So let's think about separating it out here instead. What would happen on the right-hand face? Well, the right-hand face is connected to segment 2. Hope the video can see this. Yeah, it's okay. So the shear would be opposite. We'd have something like this, VB on the plus side. It matches this one. And we'd have an equal and opposite moment, MB, on the right-hand face, right? On the left-hand side, we'd have to have equal and opposite to these, so that would be VB minus and MB, like this. So this is the free body of just a little bitty segment in between 1 and 2. Now, notice what's going to happen here. Notice that if I know the shear to the right and to the left, those shears will be equal to RB. The moments will cancel, right? Obviously the shears may or may not. Let's find out. So the shear, how do I come up with the shear to the left here? Well, I didn't write down everything I could have, right? I could have summed forces in the y direction. Why didn't I? Well, I didn't know the reaction until I went through the moment equation. Now that I've got the reaction, now I can calculate VB in the direction that I've shown it. So it would be simply RA minus the effect, the resultant of this, which, by the way, let's go ahead and calculate that magnitude. So 50 kilonewtons per meter times 1.6 meters is what? 1.6 times 50 is how much? I don't think I've got that number.
80.
It's 80? Okay, so a nice round number. So minus 80 kilonewtons from the distributed load, right? And then the way I've drawn VB, I've drawn it downward, I have to subtract VB just to the left of B, right? So from this, I can solve for VB because we know RA is 30 kilonewtons. And so VB to the left-hand side of B, let's see what would happen. Well, I'd move it to the other side. I would take 30 minus 80, and I would get negative, let's see, that's VB minus. I would get negative 50 kilonewtons. So I've drawn this in the wrong direction. In reality, the shear is upward, which actually kind of makes sense if you think about it, because this post here is supporting the beam as well, right? So you'd expect the shear to actually be upward on this left face and downward. I'm sorry, you'd expect it to be upward on the right-hand face of segment 1 and down on the left-hand face of this small segment, okay? Because RB should be pushing up. What if I did the same thing with this segment? Could I sum forces in the y direction here? Sure. We'd have RC minus 80. Of course, RC is still 30, right? And then here I've written it as plus VB on the plus side of B. I've written it in the positive y direction, right? In this case, since this sum has to be 0, VB plus would come out to, let's see, the 80 would move to the other side, so with the 30, it would come out to positive 50, and it's kilonewtons. All this is telling us is that I have drawn the shear in segment 2, just to the right of B in the correct direction. I've drawn it in the wrong direction here, but they're equal in magnitude to one another. So this VB is equal to 50 kilonewtons. This VB is actually negative 50 kilonewtons. Make sense? So if I sum forces on this small segment right in between 1 and 2, how much would the reaction be? Be 100, right? Because remember, the moments won't appear in the sum of force equation. We've got 50 pounds down on this, 50 kilonewtons down on this face, 50 kilonewtons down on this face. That means RB has to push up with a load of 100 kilonewtons. Another way of looking at this would be to say, well, let's write this down. We know RA is 30 kilonewtons, RC is 30 kilonewtons. Couldn't we take the entire beam as a free body? And couldn't we say, well, we've got this 50 kilonewton distributed load along the entire beam. We know the reaction at A is 30 kilonewtons. We know the reaction at C is 30 kilonewtons. We know we've got 50 kilonewtons per meter for a total of 3.2 meters. So the resultant load from the distributed load is going to be 160 kilonewtons, right? We just figured out that it was 80 for half of it, so 80 and 80 is 160. And now consider sum of forces in the y direction. Well, here's 60 of the kilonewtons, but we still have 160 to support, so the center support must be taking 100 kilonewtons. Make sense? Question? Yes.
Just stepping back a couple spots on
Yeah.
your some moments about MB.
Right here?
Yeah. Your 16 is going in the wrong direction. Is it pointing
16?
upwards on the left?
Well, remember that this is in this direction, which is against the sign. It can be really confusing. I see what you're saying, but this is actually the correct number. Because look, let's write it out. If we were to write out a number for MB, we would have simply written 16 kilonewton meters here, wouldn't we? But that's a clockwise. In our equation, counterclockwise is positive, so I have to plug it in as a negative.
Well, if you do that, you end up with 50 for RC.
You do for RC?
Yeah. Because for RA, you're taking the 50 times 1.6 times 0.8 minus 16, and this one, you're basically
right.
summing.
I've got a mistake in here somewhere. Now I've erased half of it, and I don't know where my mistake is. Sorry. But you get the idea, right? Basically, use the theorem of three moments to calculate the moment in the middle of the beam. Separate the beam into three segments. Your author separates it into two, but separate it into three. One with a very small segment in the middle where B is located, and then the right and the left hand. Be careful with the signs, more careful than I was apparently. And everything comes out okay. Questions, comments? Does it seem difficult or easy? Hopefully it's not too bad. You're just not familiar with it yet. Okay, let's see, I think that's it for that problem. Let's see, anything else? You know what, I could look at my sheet and try to figure out what I did wrong here. Oh, I know what I did wrong. This is right. This was wrong. Because look, we were summing moments about B, right? Still got some of the free body diagram here. The 50 kilonewton per meter distributed load causes a positive, no, this does cause a negative load. I've still got a sign error somewhere.
I think it's the RC or.
RC is positive. That should be negative. I don't know, I'll have to figure it out. I'll get back to you.
RC does come out to be 30, you have the plus 50.
Right, yeah, sure. These two have to have opposite sign, but I'm not sure why my moment needs to be plugged in negative. No, wait. Yeah, because this should be negative. We just discovered the moment of the distributed load is against this convention, or against that direction. So somehow I've got to make this positive. I don't know, if we manage to make this positive, then it would work, right? But how we would do that, what have I done wrong here? I'm not sure. I'll try to figure it out and post a comment on my own video. I don't want to waste time on it. It's there somewhere.
Maybe due to sign convention, since it's on the left-hand base at this point.
Yeah, but that's the thing. I don't think that we're using the sign, that's a good question. I don't think we're using the normal sign convention like this. I think what we're doing is we're simply considering counterclockwise positive. But that makes me question my thought. Because that was my main question about this, and something that's not real clear from your author is, what sign convention are we working with here? Are we working with this one, or just counterclockwise is positive? And I came to in looking at that other reference I have, which I'll try to scan the pages and post them for you guys as well if you'd like to see it. It's interesting, it's a little more complicated than this in a way, and in a way it's more simple. In that reference, what they do is they take the area underneath the moment diagram, and use that. It actually appears in both of these. It's a simpler form, but you have to know how to take the area beneath all those, the moment diagrams. And not only that, but it's the moment due to, as if that segment was off on its own, separate from the beam. And so that part is confusing as well. But anyway, in looking through that, I came to the conclusion that they're just taking counterclockwise as positive. But now I'm questioning that again because this one is not coming out. And unless I've made a mistake, that should be, let's see. You know what, I bet it's because I skipped this. And this seems to be the key. This is what made the reference I found very clear, and it's something that I think makes the author's version of it unclear. The fact that you've actually got this little free body in between the two separate segments. But I'm still not sure where that would come from. Somehow we've got to get this turned around like that, so we can plug it in positive and then everything will come out. But I'm not sure where that is. I'll try to find it and show it to you next time. Anything else? Okay, maybe I'm the one that needs to go back to statics. I realized what I did wrong. Remember, we started with the left-hand segment, and we calculated that this moment was 16 kilonewton meters. I've actually drawn it in the positive direction this time, okay? Because I was getting confused with the sign. I've drawn out the three free bodies. So we've got segment 1, segment 2, and the small intermediate segment. I don't need to consider any shear because the shear is not going to cause any moment in this segment because there's no length here. So if this is the positive direction for the moment on B, what's applying that moment? Well, it's this segment. So this is applying an equal and opposite moment of 16 kilonewton meters here, right? To keep this segment in equilibrium, I have to apply an opposite moment on this side. And go stepping through. And then equal and opposite on this side, right? So you see how I'm stepping from here all the way over here. So this is, in fact, a positive 16 kilonewton meter moment, right? Now let's check out that sum of forces again. Sum of moments about point B, and I should say about point B positive. So just to the right of point B, because here's point B. So just to the right, what are we going to have? Well, it should come up to 0, and it would be a positive 16 kilonewton meters, right? Minus, I'm going to have to break the line, minus the 80 kilonewton resultant from the distributed load. Remember, because this was 50 kilonewtons per meter times 1.6 meters. So 80 kilonewton resultant multiplied by its moment arm of 0.8 meters. So that's this distance here. And then finally, plus RC times 1.6 meters. Because RC has a moment arm of 1.6 meters. Now we've got opposite signs on those two. And now RC should come out to 30 kilonewtons. Okay, so grab your calculators if you would and see if it does. It should. This term will go to the other side and it will be positive. This term will go to the other side and be negative. So 80 times 0.8 would be what? 64? So 64 minus 16 would be 48. 48 over 1.6 I think is 30. Okay, so now that works. So the problem was that I tried to be fancy and draw MB in the positive coordinate direction and label it as a negative 16 kilonewton meters. But if I just drawn it in the right direction, I would end up with the right direction over here as positive, and then it would work out. So it's a simple statics mistake. Somewhere along the line, I flipped that sign, and I shouldn't have. Okay, so hopefully that helps.